Okay, in previous lectures, we talked a lot about voltaic cells, this idea that you can set up certain redox chemistry to spontaneously flow electrons and use that electron flow to do some electrical work. It turns out the opposite is also true, and that's the subject of today's lecture, electrolysis. Here, we're really driving a non-spontaneous reaction. So remember, voltaic cells, batteries, you connect a wire and electrons spontaneously flow due to the nature of the chemical reaction that can occur. But you can actually drive the reverse process and make non-spontaneous reactions happen if you use some outside intervention. And here, that's the form of electrical work to drive this reaction. Okay, so electrolysis is defined as the use of this electrical energy to create chemical reactions. And this really has been instrumental in isolating a lot of metals from the Earth's crust. That's one example. So let's look at a couple different ways this might work. There's a couple sort of seminal examples that are often used. One is sodium chloride. An aqueous solution here, really it's molten, so you have to have certain conditions met, but you can have an anode and a cathode. Remember, oxidation occurs at the anode. Reduction occurs at the cathode. Okay, and usually you would have some voltaic cell and the electrons, would flow across here. Appropriately. Now, what if instead we hook up a power source, and in this power source, maybe it's just a battery where one end is positive and one end is negative. Okay, this positive will pull electrons from this metal, right? And likewise deliver electrons to this metal. So remember, oxidation is the loss of electrons. So there's oxidations that's going to be happening in this. Remember, these are submerged here. In these submerged metal bars, cathode and anode. So if this is sodium chloride, actually what will happen here is you're pulling electrons off of this anode, this metal species. The metal does not have to be sodium or chlorine. It's usually not. It's going to be some other metal that conducts well. And you're going to pull electrons off of here, and so you're creating a bunch of positive charges here. Well, what's floating around here is chlorine. So these negative chlorine ions are going to come by here and neutralize this electron, and they're going to become chlorine atoms. And there's another one over here that's going to be neutralized at the bar and become chlorine atoms. And chlorine is a diatomic. So chlorines will be pulled out of the solution, neutralized, and make chlorine 2 gas. So you will start to see in this sodium chloride molten solution, chlorine start to bubble out, right? And likewise, there's sodium plus. There's a bunch of electrons on this bar. Why? Because you have a potential difference here from a battery or something that's providing electrical work and pushing electrons to these metals or pulling the electrons away from the anode. And sodium plus can swing on by and pick up an electron and make solid sodium, or I guess in this case, liquid sodium. Right? At the certain temperature conditions, you have to operate this. So, usually in nature, we find sodium and chlorine like this as sodium chloride, but now we can extract and synthesize chlorine gas using electrolysis, putting in work, right? Naturally, sodium chloride aqueous doesn't spontaneously make liquid sodium and chlorine gas, right? That's non-spontaneous, but by putting in the work, we can drive a reaction that's usually delta G positive 0, and we can make it occur. And sometimes we're willing to spend some energy to get certain compounds like chlorine and sodium isolated. Another example of this I'm not going to draw in detail, but another example of this is nickel. And you can have a solution of nickel 2 plus. You can have a nickel anode here. And you can hook up a battery again. And down here, you can have a steel object, like a steel ring, like a wedding ring or something. And what happens is the nickel 2 plus will go into the solution because you've pulled away its electrons. And these nickel 2 pluses will migrate over and coat the steel ring because there's a bunch of negative charges building up. And so what you're doing here is essentially electroplating or plating, nickel plating steel. So that's another example of something you can do with electrolysis. Okay. In both cases, if you just put steel in a bath of nickel 2 plus, it doesn't plate it. You have to sort of drive this chemistry to happen. Okay. One final example that I think is a cool artificial, a cool use of electrolysis is the history of the Washington Monument. In 1882, we constructed and built the Washington Monument. And if you're familiar, it's this very tall column in Washington, D.C. And on the top, it is pointed. And on the very top up here, we capped it with aluminum metal, solid aluminum. The biggest chunk of aluminum at the time in the world of 1882, the biggest chunk of aluminum that ever been synthesized. Now, at the time, aluminum was very, very expensive. Okay, aluminum cost the same as silver back in 1882. And so we wanted something that was super precious, so we chose aluminum and put it at the top of the Washington Monument. Okay, it turns out in 1886, Charles Hall, at the age of 21, used electrolysis, like we just talked about, but used it for aluminum. And he was able to synthesize pretty cheaply solid aluminum from aluminum oxides and other minerals from the earth. It used to be really energy intensive to isolate aluminum, hence why it cost so much, the same as silver in 1882. But then Charles Hall came along, used electrolysis, used chemistry, created a bunch of aluminum solid. And so aluminum's price dropped incredibly. And the top of the Washington Monument went from something being so precious. They put this on display at Tiffany's jewelry store. It was so nice and valued and precious. They put it on the Washington Monument. 4 years later, the price of aluminum incredibly went down thanks to electrolysis. And now we have a cheap, but still, I guess, impressive in some regard, cap to our Washington Monument. Okay, so even though aluminum is the third most abundant element in the Earth's crust, it cost a lot at the time because of how we had to isolate it. Charles Hall fixed that problem, and now we have aluminum everywhere. Now, we, with this qualitative information, can quantitatively calculate exactly how many grams of, say, aluminum we could create by hooking up a battery and running a certain current for a certain amount of time. So now we're getting into the mathematics here of being able to calculate exactly how much current we have to deliver, or exactly how much time we have to deliver that current in order to electrolyze and form some grams of substance. Okay, so the things to point out here is that it's about the total charge you're moving. And the total charge you're moving, Q, is going to be, it's shown here, current is I, time is T, but this is the amps times the second, okay? That's a coulomb, the charge. And in these problems, you're generally told the amps and the seconds, and you have to navigate all the way to grams, or you might be given the grams and the amps and have to solve for second, or given the grams and the second and have to solve for amps, okay? It's about working this way or this way. So let's look at each of the steps, okay? If you're given amps and second, you can calculate the total charge that you need to move. We also have Faraday's constant, that is 96485 coulombs per mole of electrons. So if you know the coulombs in step 1 up here, step 2, you can take that coulombs and do some straightforward dimensional analysis. So whatever X number of coulombs you've calculated in step 1, you divide that by 9645 coulombs to get a mole of electrons. X moles of electrons. That's step 2 here. Step 3 is taking that X moles of electrons and using some molar ratio. What you need is moles of electrons to moles of substance. Maybe that's aluminum, maybe that's nickel, whatever it is, right? We'll just call it moles of aluminum here. This ratio and these numbers, right? Is it 2 moles of electrons to 1 mole of aluminum? Is it 3 to 1? Is it 2 to 3? What is this ratio? This ratio comes from the balanced half reaction. So you have to consider what is the actual redox chemistry happening, set up a half reaction, and then look at that half reaction to understand what the ratio is. We'll see this in examples to follow. Okay, so that's step 3. At the end of step 3, you will have some moles of substance. Step 4 is the easiest of them all because you take that moles of substance and you multiply by the molar mass. Here, if it's aluminum, 26.98 grams per mole. And then you get your grams of substance at the end, which is what we want. Now, like I said, you could be given grams and have to go the opposite way through the table. So you'd be dividing by the molar mass. You'd be just going backwards through these steps to calculate either the amps or the seconds. So let's look at electrolysis in some of these practice problems in different ways they can be asked. Calculate the number of grams, so we're going down this chart, of aluminum produced in 1 hour by electrolysis of molten aluminum chloride if the electrical current is 10 amps. Okay, an amp, by the way, is a coulomb per second, so you want to make sure your time is in seconds. Okay, 1 hour, 60 minutes, 60 seconds in a minute, so 1 hour is 3,600 seconds. Okay, so again, step 1, we're given current and time, so we're going to multiply those two things together. My 10 amps, right, where an amp is a coulomb per second, multiplied by my 3,600 seconds. I've determined I have 36,000 coulombs. That's the number of charges I need to move. Now, Faraday's constant lets us take this 36,000 coulombs and convert it to moles of electrons. 96,485 coulombs and 1 mole of electrons. So this dimensional analysis leads us to 0.373 moles of electrons. Step 3 is where I have to get the redox chemistry involved. Here, it's given to you for free in this these half reactions that are already balanced. So let's take this 0.373 moles of electrons. And I needed to convert this from moles of electrons to moles of, I'm asked for aluminum here, so moles of aluminum. Right, solid aluminum. Now, from the balanced equation, there are 6 electrons for 2 solid aluminums. So it's 6 moles of electrons to 2 moles of solid aluminum. Carrying out this 0.373 times 2 divided by 6, I get 0.124 moles of aluminum. Okay, so those are the first 3 steps. The last step, I think, is the easiest. You take this moles of aluminum and multiply it by the molar mass for aluminum, 26.98 grams per mole. And this should give you 3.36 grams of aluminum, which would be the final answer here. Okay, so there's one practice problem. You could be asked this another way. Remember, you could be given grams and asked to solve for time or amps. So let's see a problem like that. How many amps are required to plate 13 grams of chromium from a chromium 3+ solution in a period of 8 hours? I'd encourage you to pause the video here and try this yourself before you watch me solve it. Okay, so I need to solve for amps, and I'm given 13 grams of chromium. So if I'm given the grams, I know I'm going to need to be going in this direction. But even if you don't have this or have memorized this chart, just start with the grams. Okay, 13 grams of chromium. What can you do with 13 grams of solid chromium? Well, you can convert it to moles of solid chromium. That's something we know. We have a periodic table. 1 mole of chromium is 52.00 grams of chromium. (13 divided by 52 gives me 0.25 moles of chromium. Next, I'm going to take that moles of chromium more dimensional analysis, so I know moles of chromium is going to go down here, so it cancels. What do I have? Well, I have time, amps, that doesn't work, but what is this? Chromium from a chromium 3+ solution. So I'm starting with chromium 3+, and I'm making solid chromium. The charges don't balance here. There must be 3 electrons here involved, right? So this is reduction, it's gaining electrons. Chromium 3+ aqueous, gaining 3 electrons and making chromium solid. And now I realize that I have a ratio here the 1 is implied here, of 3 to 1. So this is 1 mole of chromium per 3 moles of electrons. Next calculation then is let's get rid of moles of electrons. I need to get to charges, and I remember Faraday's constant, 96,485 coulombs per mole of electrons. So this tells me the total charges I need to move, 72,364 coulombs. And I also remember that an amp, which is what I'm after, how many amps? An amp is a coulomb per second, right? Or said another way, coulombs is amps times seconds. And that's what it says up here. So if I have the coulombs, 72,364 coulombs, I need to divide it by the seconds to calculate my amps, right? I'm going to take this 72,364 coulombs, and I'm going to divide it by 8 hours. But I remember my time has to be in seconds. So the denominator is going to be 8 hours and 3,600 seconds in an hour. You can do all this math separately if you want. You should get a number of seconds here in the denominator of 28,800 seconds. 8 times 60 times 60. So coulombs divided by this many seconds gives me the amps, and it should come out to 2.51 amps. So here are 2 different types of electrolysis problems. Quantitatively figuring out how many amps we have to deliver for a certain amount of time to get a certain amount of chromium, or how many grams of aluminum we can produce with a given setup of amperage and time. And this is commonly used to plate steel with nickel or synthesize chlorine or aluminum, and gives us a lot of materials that we find now affordable and cheap in our everyday lives. So that'll do it for this lecture. See you next time.